Hi, everyone. I'm very excited to be here today to talk about a piece of my doctoral research, which I'm calling the hidden energy costs of set it and forget it parameters in heating, ventilation, and air conditioning operations, also known as HVAC. In my PhD, I focus on reducing energy consumption of air conditioning in existing commercial buildings, and I chose this focus for two reasons. First, 12% of global final energy demand was used to heat and cool commercial buildings alone, and this is a significant portion of total global energy demand. The second reason is almost 50% of existing commercial buildings in the US were built before 1990, and these older buildings often have older HVAC systems which have limited controls, and which would need significant amounts of investment in order to update. While newer buildings usually have smart thermostats, adjusting set points in older buildings can require someone to walk into a closet and manually change the set point. The older systems rely on set it and forget it set points, which can handle the worst case scenarios. You may be thinking, why don't we just install smarter controls? Well, that's expensive, and these older buildings are often underfunded, so we need low-cost solutions to reduce their energy use. Air conditioning in commercial buildings controls temperature, humidity, and ventilation, but my work focuses on the first two of these. Air conditioning controls both humidity and temperature by cooling down the air to control humidity just to warm it back up to a comfortable temperature. Yep, you heard me right. Air conditioning cools down air just to warm it back up. Seems inefficient, right? Well, it is. But it's also convenient. But this convenience comes at the cost of both energy and comfort. Set it and forget it set points, which are used in these older buildings with limited controls, are the same across the United States, even though the climates vary significantly. Here on the right, we see a map of the climate zones in the US, and generally temperatures increase from north to south, and humidity changes from east to west. The worst case scenario, which is the set it and forget it set points are tuned to, is synonymous with how hot and how humid it gets outside. This worst case scenario happens infrequently and changes based on where you are. In Houston, it gets very hot and very humid, whereas here in Palo Alto, the worst case scenario is not as extreme. So how can the set it and forget it set point be the same everywhere? Well, it shouldn't be. The set it and forget it set point was decided decades ago, when energy was cheap and there was much less concern with climate change and wasting energy. I'm teaching old buildings new tricks by using what's already there in a different way. My work considers the actual outside air conditions at a building's location and increases the set points by 4 degrees Fahrenheit when the outside air isn't humid enough to require the set it and forget it temperature. In this case, there's no need to cool down the air as much because there isn't enough water to condense. This work considers between 2 and 12 changes to the set points per year, because more frequent set point changes than monthly become infeasible to implement at these older commercial buildings. So I'm reducing these inefficiencies by using two different tools. The first of these tools is a NASA MERA-2 weather dataset, which has actual outside air conditions, including humidity and temperature, for the entire US at a resolution of 0.5 degree latitude by 0.625 degrees longitude parcels. By using actual outside air conditions, I can determine what the real worst case scenarios are in each of these different parcels to avoid overcooling when unnecessary. Along with this data set, in my PhD, I ran no-cost experiments in commercial buildings in Texas, New Jersey, and California, which are highlighted by these X's. In my experiments, I increased the set it and forget it temperature set point by just 4 degrees Fahrenheit and found this 4-degree increase saved up to 10% of the cooling energy used by the air conditioning in the buildings in which I ran experiments. The second tool I'm using is based on a data-driven, physics-based model, which I developed during these experiments to understand the energy impacts of implementing these adjusted set points. Here, I'm showing you the comparison of the model results and the actual chilled water load from the experiments run in Texas. As you can see, there is pretty good agreement. Unfortunately, we don't have time to dive into all the details of the model right now, but if you'd like to learn more about this, please find me afterwards. With the two tools, I have now estimated the percentage of energy savings possible across the US if older commercial buildings with limited controls implemented these techniques. I've placed an example building described by the model in each of the parcels for which there is NASA weather data, and estimated the energy consumption under baseline operation and changed set point operations based on my experiments. This table on the left shows the set point change scenarios considered, where the number represents how many changes are considered per year, and the letter represents when in the year the set point changes occur. Here we can see the results of normalized cooling load saved across the United States from these scenarios. The normalized cooling saved is a function of both the energy saved and the number of days a year those savings are seen. As the number of set point changes increases, the savings are seen further east, and we see up to an 18% reduction in cooling load required by changing set points as few as 12 times a year. Now, if we take the monthly set point changes and compare those savings to the possible savings from sophisticated controls, in other words, a system that can change the set point every day, we can see that a large fraction of the possible savings is feasible just by changing the set points monthly. If we look at each of the different scenarios, we can see that we can save between 18 and 45% of the total savings as compared to changing set points every day, with significantly less effort on the part of the operators. So I've successfully found a low-cost, easy-to-implement, and high-impact solution for reducing energy consumption of older commercial buildings. In other words, I've shown you can, in fact, teach an old building new tricks. My next steps are now to harmonize this work with 2 additional data sets in order to understand the magnitude of energy savings possible. One is the Commercial Building Energy Consumption Survey, which is administered by the U.S. Energy Information Administration and was most recently administered in 2018. The second data set is the University Campus District Energy Consumption Survey, which I presented about at last year's Stanford Sustainability Data Science Conference, and I'm happy to talk more about it offline. But basically, UCDEX is a data set that I created which has daily level heating and cooling data from 40 universities across the United States. With these additional data sets, I can now understand what the actual energy consumption is of commercial buildings in the US at a daily resolution, and then understand what the magnitude savings is of implementing these updated set it and forget it set point changes approaches across the United States. I'll leave you with these 3 main takeaways. First, so there's a large potential for savings from HVAC energy consumption from updating those outdated rules of thumb that do not consider the actual outside air conditions in HVAC operations. Second, these results are backed by experiments in 3 climate zones from which a data-driven, physics-based model was validated and used to understand the potential of implementing these approaches across the United States. And finally, the results show a large amount of possible savings is achievable with just monthly set point changes, and future work will focus on understanding energy magnitude impacts by harmonizing data sets at different resolutions. Thank you again for your time, and I'd welcome any questions.